Okay, so now we're going to move on to the next step in proving this theorem. And so the general proof will follow from induction on n. So we're going to suppose that this works when you have n terms in the sequence, or I guess n plus 1, but for a certain value of n. And then if you increase it by adding one more term so that this condition is still satisfied, then this property will still hold. So first, technically we still haven't proven it for one term. We've only done the Dirichlet integral, which is when a0 is equal to 1. So let's start off by proving that case. Then we'll prove when there are two terms. So that'll be when when n is equal to 1 and you only have two numbers. And that'll give you an idea of how the general proof will go, and then we'll go over the general proof by induction. So the first thing we want to show is the integral from 0 to infinity of sine ax over ax dx is equal to pi over 2. So I said this is the same thing as this integral up here, except you ignore the higher terms because there's only one term. And I just wrote a instead of a0 for convenience. And so now to evaluate this, we want to somehow convert it into the Dirichlet integral because we know what that is already. So we can rewrite this as 1 over a integral from 0 to infinity of sine ax dx over x. So this dx over x may seem weird, but there's a useful reason for doing that, which we'll be using over and over again later on. And so here what we want to do is convert this into an integral that looks like the Dirichlet integral up there. So the obvious thing to do is to do a u substitution to get rid of the ax inside the sign. So you can do something like u is equal to ax. So then notice that two things happen here. We have x is equal to u over a, and dx is equal to du over a. So now if you take the ratio dx over x, then all that is du over a over u over a, and then the 1 over a in the numerator and denominator cancels, and so all you're left with is du over u. And then this sine of ax just becomes sine of u because u is ax. So this can be rewritten as 1 over a times the integral of sine of u du over u. And then what are the bounds of the integral? Well, when x is equal to 0, obviously u is also going to be equal to 0. And when x increases to a really large positive number, then because a is positive, which I should have put up here, but that's one of our conditions of the problem. Since a is positive, and if x is a really large positive number, u will also be a very large positive number. So this will still come out to be positive infinity. And so this is your Dirichlet integral that we had before. And all you have here is pi over 2a. And yeah, I forgot. Yeah, this should be a 2a. So if you think that like this dx over x is equal to du over u is a bit coincidental, there is actually a deeper reason behind it. So I'll just go off on a bit of a tangent. So if you have some integral of the form like integral of f of x plus a dx, when you want to change that, if you know like the integral of f of x and you want to change it to something else so that you can evaluate it easier, what you would usually do is something like u is equal to x plus a, and then you have that du is equal to dx. So here what you're doing is you're sort of translating x to the right by adding a constant to it, and then that leaves dx equal to du. And in this situation, what you're doing is you're taking like f of ax and you're integrating that times dx over x. So now if you say u is equal to ax, then we just show that du over u is equal to dx over x. So then this integral up here is the integral of f of u du with potentially different bounds of integration. And this integral here is equal to the integral of f of u du over u. So this invariance comes from what is called a Haar measure. So a Haar measure is sort of a way to measure how large a certain set is, and you can use that to define an integral. And so this is called an invariant Haar measure, or an invariant measure under like some operation. So this dx equals du comes from the fact that you have a Haar measure dx, which is invariant under translation, and it corresponds to the real numbers as a group under addition. And dx over x is similar. It's a Haar measure corresponding to the real numbers, well, the multiplicative real numbers, which is the real numbers without 0, as a group under multiplication. So essentially what that means is like this thing, if you do use substitution by scaling it up by multiplying by a number, then it leaves this thing invariant. And if you do a use substitution here by translating it by a number, then it leaves the integration thing invariant. So if you want, you can search a power measure if you're more interested in that. But anyway, this proves our first claim that this integral is equal to pi over 2a. So I'll just put that to the right, and then I'll get to the next part of the problem. So now what we want to do is prove this for n is equal to 1. So you have two numbers. And instead of calling it a0 and a1, I'm just going to call it a and b for convenience again. So what we want to show is the integral from 0 to infinity of sine ax over ax times sine bx over bx is equal to, well, dx is equal to pi over 2a, where a is greater than b is greater than 0. Okay, so what we will do to prove this case is sort of take it in an indirect way and use that same sort of switching the integral sign that we had before to show the Dirichlet integral, but it's going to be in a sort of separate manner. So what we'll do is we'll start off by looking at the integral from 0 to infinity of sine ax over ax times sine of yx dx. So y we're going to consider to be some positive real number, and we are going to integrate with respect to y, just like we integrated with respect to y earlier, but y was like an exponential thing. Oh, that should be cosine. Okay. So what we want to do is convert this again into some form of either the Dirichlet integral or the other integral that we just evaluated. So we want to get rid of sine ax and cosine yx and put those into some form of sine. And so what you can do is you can use your trigonometric relations. So you have sine ax plus yx is equal to sine ax cosine yx plus cosine ax sine yx. And you can also look at if you change the sign to a negative sign, so it'll be sine of ax minus yx, and this will be sine ax cosine negative yx plus cosine ax sine negative yx. Okay, so because cosine and sine are even and odd functions, cosine of negative x is cosine of x, so you can ignore the negative sign there. And sine of negative x is negative sine of x, so you can get rid of that negative sign from the inside and put it out here. So now what we want to do is isolate sine of ax cosine of yx. So what we can do is add these two together. So if we were to add these two things, then this will cancel out with that because it's the same thing with the negative sign. And you end up with twice sine ax cosine yx. So essentially what we have is 1/2 sine ax plus yx plus sine ax minus yx gives you this sine ax cosine yx that we have up there. And we will use this and substitute it into our integral. So since we haven't taken care of the ax yet, we still have to divide by ax. But I'll do some rewriting again to make it look like what we did before to prove that second identity up there. So write this as 1 over 2a integral from 0, actually 1/2 integral from 0 to infinity of this divided by a dx over x. And now we sort of have two integrals of that form, so we can split this up into the integral of the first thing and plus the integral of the second thing. So this will be So what we have is just splitting up this integral, we have sine of a plus y x over a dx over x plus 1/2 sine of a minus y x over a dx over x. So again, we can do a u substitution to try to get these integrals down to something that looks like this. And if we do that to the first integral, what we get is u is equal to a plus y times x. And so we know that dx over x is equal to du over u because of what we did earlier. And if we look at our bounds of integration, what we're going to get is that if x is equal to 0, then u is also equal to 0. And because a plus y, since y is a positive number, like I said earlier, a plus y is also going to be positive. And so as x increases to a really large positive number, so will u. So this integral will become the 1/2 integral from 0 to infinity of sine u over a du over u. And you can notice that this is the same thing as our expression up here. So we can just substitute that down here to become pi over 2a, but then you also have a 1/2. So this part will essentially evaluate to pi over 4a. So now we just need to focus on what the second integral will be. And again, you want to do a u substitution, u is equal to a minus yx, and do a similar sort of thing that we had earlier. So I'll write it up here, I guess. Okay, so what you want to say is u is equal to a minus y times x, and then dx over x is equal to du over u. Great. Now we can just rewrite this integral as 1/2 integral sine u over a du over u. And so here, now we have to look at the bounds of integration. So we actually have three cases. The first case is if a is greater than y. Then a minus y is a positive number. And as x becomes really large, u also becomes really large. And so the bounds of integration will be from 0 to infinity. So case 1 is a is greater than y. Then you have that this is 1/2 integral 0 to infinity of that stuff du over u. And so this is going to evaluate to pi over 2a, and then you have the 1/2. This will be pi over 4a. Second case is if a is equal to y. This is actually the easiest case because you have, looking at your original integral, a minus y x. A minus y is just 0 if a is equal to y. And so you have the integral of sine of 0x over a, but sine of 0x is always just 0 because sine of 0 is 0. And so you have that this is just the integral of 0, and that's equal to 0. So you have the case a equals y, you have the integral from 0 to infinity, 1/2 sine 0x over a dx over x, but this is going to be equal to 0, so this whole integral is equal to 0. Now the third case requires a bit of care, and it's the case when a is less than y. So when you have a is less than y, when x is equal to 0, obviously obviously u is also going to be equal to 0, but as x becomes a really large positive number, u is going to be a very large negative number. So for example, if x is like 100 and a minus y is -1, then u is going to be equal to -100. So what that means is that your bounds of integration change from 0 to infinity to 0 to -infinity. Okay, so now you want to evaluate, that should be an a. So now you want to evaluate this integral. And to do that, you might want to make another u substitution, or I guess a v substitution in this case. So we can say if v is equal to minus u, then if u becomes a very large negative number, v becomes a very large positive number. So that'll fix our bounds of integration and change it back to 0 to infinity. So we can set v is equal to minus u. And notice this is still multiplying your variable by some constant. So that means that we can also use the same trick, du over u equals dv over v. And then for this case, what you get is that this integral becomes the integral from 0 to infinity of sine negative v dv over v. And then sine of negative v, since sine is an odd function, sine of negative v is negative sine of v. So we can move this negative sign to the outside. And then you have this integral, which is the same integral as up there. And it's pi over 2a, but then you have this negative 1/2, so it's negative pi over 4a. Okay, so to conclude, we have three cases. We have if a is greater than y, then the second integral evaluates to pi over 4a. If a is equal to y, we have that this integral evaluates to 0. And if a is less than y, the second integral is negative pi over 4a. So what does that mean for our original integral up here? So we can split this up into three cases. So we have that if a is greater than y, then we have that this integral is pi over 4a plus pi over 4a, so that is just pi over 2a. Second case is when a is equal to y, so that is going to be pi over 4a plus 0, so that's just going to be pi over 4a. And the last case is when a is less than y, and here you have that this integral is pi over 4a, but this integral is negative pi over 4a. So then these two integrals will cancel, and then you get that it's equal to 0. So now we're going to use this function, sort of, and we're going to call it a function of y. So let's call this function f of y. And notice that if you graph out f of y, it'll look something like this. Okay, so at a, you have a discontinuity where it goes from pi over 2a to pi over 4a, so it goes halfway down. And then after that, it goes down to 0. And so this integral up here, even though like none of these expressions have a y in it, you have to remember that implicitly this is still a function of y, because as you change the value of y, this integral value will change. So I'll rewrite the board a little bit, and then we'll integrate this a little bit more and finally get our solution for this integral. So again, we have this integral here, which we evaluated into three cases: when a is less than y, when a is equal to y, and when a is greater than y. Sorry, this should be switched. And so now we can look at evaluating this integral. So it's the integral of this thing with respect to y, as y ranges from 0 to b. So this is pretty much the area. You can evaluate this in one of two ways. First, you can realize that the inside of this is your f of y that we have defined here. So this is going to be equal to the integral from 0 to b of f of y dy. So this is just your integral of this function, which is like, you can interpret it as an area. So we see that this splits into two cases. So if b is less than a, then what happens is you are integrating somewhere in this region. And all that gives you is the height of your rectangle times its base. So you have pi over 2a times your horizontal length, which is b. And this evaluates to pi b over 2a. Now if b is greater than a, then what you have is you have this whole rectangle. and then you have some length here, so like say this is b. This length here though, the function is 0 there, so it doesn't contribute to the integral. And all you have is the area of this rectangle, which is a times pi over 2a, which will just give you pi over 2. So notice all that we care about is the case when b is less than or equal to a, because that's what we have up here. So we only care about this top integral, which is pi b over 2a. So I'll just write that down to the right. So now the second way that we can evaluate this integral is by switching the bounds of integration. And again, I won't go into too much of the details as to why you can, but you can. So you can integrate with respect to y first and then integrate with respect to x. So let's see what happens then. Okay. So in this case, what you're doing is you are integrating the same thing, but you're integrating first with respect to y from 0 to b, and then you're integrating with respect to x from 0 to infinity. And so what you can see is that since you're integrating with respect to y first, you can really treat sine of ax over ax as a constant because there's no y that comes up here. So what you can do is you can consider that as a constant and move it outside the integral. So that what you get is the integral from 0 to b of cosine yx dy dx, and then the sine of ax over ax. Now when you evaluate this, you'll find that it is the same thing as, so integral from 0 to b of cosine yx dy, that is just going to be equal to negative, it's going to be equal to positive sine of yx over x evaluated from 0 to b. So this is just, if you differentiate sine of yx, then you get x times sine of yx if you differentiate with respect to y. And so you just divide by x to cancel that out, because in this case we're treating x as a constant. So now if we substitute that y is equal to b, then you get at the top limit sine of bx over x. And if you substitute in y is equal to 0, then you get sine of 0x over x. But sine of 0 is always 0, so then that'll just evaluate to 0. So this is what your inside integral evaluates to. So finally what you have is that this is the integral from 0 to infinity of sine ax over ax times sine of bx over x dx. So yeah, we just evaluate this inside integral. It turned out to be this, and we just put that out there. So now this is very close to what we want up here, right? Except all we're missing is this b from the denominator. But that's okay, because we have that this is equal to pi b over 2a, so long as a is greater than or equal to b. And when a is greater than or equal to b, this is true. So what you can do is you can just divide through by b on both sides, and then you can move the b from up here down to there. So get rid of this equal sign there. Get rid of b, divided by that, and bam, we have this statement that we claimed to have proven. So now we've proved the case when n is equal to 0, which means that you only have one term here, and when n is equal to 1. So you have sine of ax and sine of bx, or sine of a0x and sine of a1x. So now I'll clean the board a little bit, and then I'll get to the general proof. And I encourage you to try and work it out yourself a little bit if you are so inclined, because the proof is very similar. It uses sort of integration by cosine of yx. And the only difference is that you need to be a little bit clever with this condition. So you assume that works from a0 up to an for any values of a1 through an that satisfies this condition. And then you add on another term, an plus 1, that still satisfies that condition. And then you try to manipulate your things by turning this into like a sum of two sine integrals. And then you split it up and work through that and try to do that. So I encourage you to try and pause it and figure it out on your own. And yeah, we'll get to the general inductive proof now. Okay, so now we're finally going to prove this claim in general. And so as I said, we're going to prove this by induction. So we're going to assume that this claim holds for n terms. So I just put 3 dots here because I don't feel like writing out this whole product. But like you have sine of a0x over a0x, sine of a1x over a1x, sine of a2x over a2x, all the way up to sine of anx over anx. And we're going to assume that that's equal to pi over 2a0 if a naught is greater than a1 plus a2 all the way up to plus an. And then we are going to use that, and we're going to say if we add on another term, an plus 1, and if a naught is still greater than a1 plus a2 plus all the way up to an plus 1, then we're going to show that this integral is still pi over 2a0. So how does this prove this entire claim? Well, we already proved it for the case where there's only one term. But if you don't like that because, you know, the second condition, you can ignore that if there's only one term. We also proved it for the case where there are two terms. So you have a0 and a1 with a0 greater than a1, and that's what we just did. So if you put that together with this, then since we proved it for two terms, this step will prove it for three terms, and they'll prove it again for four terms, and so on and so forth. And so we'll prove it for all positive integers n, which is what we want. So moving on with the proof, we're going to do a similar thing that we did last time, which is we're going to take this integral and multiply the inside with a cosine function of with a positive parameter, and then we're going to evaluate that and then take an integral of that again. So what we have is this integral up here. So notice how we don't have the an plus 1 term yet because that will come later. Instead, we threw in a cosine of yx term. And what we want to do again is get rid of the cosine so that it looks something more like this. So what we'll do is we'll combine this first term and this cosine of yx using a similar method that we did before. So we know that sine a0x cosine of yx is equal to sine of a0 plus y times x plus sine a0 minus y times x, all of that divided by 2. So that just follows from the same thing that we did last time, except now we're using a0 and y instead of a and y. So if we substitute that into here, we can split this into two integrals, one with a0 plus y and one with a0 minus y, and then we have some extra terms. So I'll just write that out. Good. So what we have here is we just put this down into these two integrals. So we factored out the 1/2, and we replace this as sine of a0x with sine of a0 plus yx or sine of a0 minus yx. And then I also took this denominator divided by x and moved it to the end here, dx over x. And by now you should know why we're doing that. So now again we sort of want to see what this can evaluate out to. And so the first one is okay, so last time I showed you the different cases of what happens when y is related to a in different ways. You can do the same thing here, but that just involves a lot of algebra. So for simplicity, we can assume that y is going to be less than a n plus 1. Since eventually what we're just going to be doing is integrating this function from 0 to a n plus 1, like we did last time from 0 to b. And since a n plus 1 is just one point at the end, it doesn't really make a difference to the integral, even if that would evaluate the integral, these two integrals differently. So here now we can make notice some things based on this relation here. So if we look at a0 plus y, we have that a0 plus y is greater than or equal to a0, which is greater than a1 all the way up to an plus 1. a1 plus all the way up to an plus 1. And because an plus 1 is a positive number, even if we get rid of the an plus 1, this will still be a smaller positive number. So like say an plus 1 is 0.5 and the sum is 5, then if you get rid of the last one, it's still going to be 4.5. So this is going to be greater than a1 plus all the way down to an. Okay, so what we have is this first integral is the first term is greater than the rest of the terms. And so because of this and our assumption that this is true, this first integral just evaluates to pi over 2a0 times 1/2. So that'll be pi over 4a0. Okay. And looking at the second integral, you can make another similar assessment. So you can say a0 minus y. So this one's a bit more tricky because you have to use this fact that y is greater than y is less than an minus 1. So like if an plus 1. If an plus 1 is like 1 and y is 0.5, then if you subtract off 0.5, that's going to be greater than subtracting off 1. So a0 minus ay is greater than a0 minus an plus 1. But then if we look here, that is greater than a1 plus all the way down to an plus an plus 1, which is from here, and then minus an plus 1, which is from here. And then these last two cancel out, which means that you have a0 minus y, which is your first term here, is greater than the sum of all these other terms. And so again, by our induction thing, this should also evaluate to pi over 4a0. Well, it's pi over 2a0, but then you have the 1/2 factor. So then adding those two together, we get that if y is less than an plus 1, this evaluates to pi over 2a0. So now we're already almost done with the problem. All we have to do is integrate this function with respect to y from 0 to an plus 1. So if we integrate this integral, so 0 to an plus 1, integral 0 to infinity sine a0x over a0x. Okay, so here we can again evaluate this in two ways. First, we can simplify this expression on the inside, and since we notice that y is between 0 and an plus 1, we have this condition, and under those conditions we saw that this integral is pi over 2a0. So we can plug that in, and this is just the integral from 0 to an plus 1 of pi over 2a0 dy. And then this integral is just the area of a rectangle, which is pi an plus 1 over 2a0. Okay, but now you have that this is the same as switching the order of integration of this. So you integrate with respect to y first, and then you integrate with respect to x. And so if you do that, what you get is that this is equal to So you have, by switching bounds of integration, you have dy dx, so in that order. And now you're integrating first dy with respect to y from 0 to an plus 1, and then with respect to x from 0 to infinity. So now again, all of these terms only depend on x, they don't depend on y, so you can consider them as a constant when you take this first integral. So you can move this integral over to the right. And it's pretty easy to check that if you evaluate that out, this integral becomes sine of an plus 1x over x. So again, you just treat x as a constant there, and you integrate with respect to y, and you get sine yx over x. And then after you plug in your bounds of integration, that is what you will look at. Now, we have that these two things are equal to each other, so you just ignore that. And then you erase the an plus 1 up here, move that to down here. And there we go, that completes our proof. So we just showed that with this assumption, we broke down this integral into two different integrals that added up together into pi over 2a0. And then we integrated this function from 0 to an plus 1. And then by switching the bounds of integration, we proved this inductive step. And that proves that this formula holds for all positive integers. And so this is a pretty interesting result. You might be wondering, well, what happens if this number exceeds the first value? If you're interested, you can search up something called the Borwein Integral online. They figured out a general formula for it, but it's quite messy. I haven't read through the original paper myself, but I'll probably put it down in the description. And also, there's another interesting way that some others looked at it, is that you can somehow look at the integral of this product as a sort of convolution of different functions together. And so if you do that, if these terms are less than your first term, then some of the properties of your function are preserved, otherwise they aren't. So I'll probably also put a link to something that talks about that in the description as well. But yeah, that concludes it for this video. We proved this pretty interesting statement using some fancy properties and induction, and I hope you enjoyed it.